Pluto, a far-off and baffling smaller planet, was once an individual from our solar system's planetary family. However, later alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a stunning disclosure. They recommend that this frosty world is on a potential crash course with Neptune. But how could this happen, and what might be the outcomes of such an enormous event? Are we seeing an interesting cosmic phenomenon? Or is there something else to this looming infinite crash? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, a previous planet that was downgraded to a dwarf planet, partly due to its curious orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading researchers, Pluto's trajectory is perilously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the warning of a potential dangerous crash between these two planets that could be an immense threat to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike any other planet in our nearby planetary system. It requires a stunning 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, diverging entirely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, calculated at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its convergence with Neptune's. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, resisting what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to grasp its unique path. Unlike the other planets, whose orbits lie somewhat near the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all cooperate in a complicated way. Terms like asymptotic libration and scope libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a kind of libration. Regarding Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an extra layer of protection from potential impacts. Another critical factor in this situation is the VZK oscillation. This is named after three researchers, Vav Zappel, LV, and Kai, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move. In Pluto's case, VZK helps us understand why its path around the Sun is so strange. Despite the apparent chaos, this oscillation helps keep Pluto's orbit stable. From here on, for an extraordinarily long time, the VZK oscillation shows that, even though things in space may seem wild and random, certain patterns and rules keep everything in place. All of these parts help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or stray off course. This three-body problem helps in understanding how these orbits change due to the way space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that, Despite these stable properties, Pluto's orbit is actually turbulent, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos under control. Recent computer tests have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a large part in protecting Pluto's orbit. What's more, Saturn helps overall too. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for an extremely long period, possibly even billions of years. It's as if Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are vital in the larger context of the universe, for maintaining the order and consistency of celestial bodies' movement. Without these components, the solar system, as we know it, would be a place of far greater turmoil and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to a domino effect on other celestial bodies. For Pluto, particularly with discussions about it possibly colliding with Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also shows the importance of constant observation and study of these phenomena to better grasp our place in the universe. Investigating the depths of space often leads us to confront the eccentric nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using virtual simulations has been incredibly helpful for researchers to figure out how Pluto moves in space. These simulations use intricate math to mimic how Pluto, along with other space objects like Neptune, pull on one another. By adjusting small details in the simulations, astronomers can see how even tiny changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations showed something really interesting about Pluto's orbit. Despite having mechanisms like asymptotic and scope libration to keep it stable, its orbit can still be wild and unpredictable if you start with even a tiny difference in where Pluto is or how fast it's moving. Over many years, its path can end up looking very different. However, despite this chaos, Pluto's orbit remains stable for a long time, billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it seems all over the place at first. Predicting large events, especially when they involve chaotic orbits like Pluto's, presents huge challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a strong tool to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or distortion can lead to drastically different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made huge strides in understanding space, the case of Pluto reminds us of how our knowledge of the universe still remains limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have sweeping effects, influencing the stability and trajectory of other bodies within the system. So, why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune, despite all these complex forces working to prevent such an event from occurring? Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the captivating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unexplored reaches of space. Tyson's position on Pluto's renaming is rooted in the ever-expanding knowledge of our solar system. He sees the renaming as not a downgrade, but rather a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He views the intricacies of Pluto's orbit, as well as its interactions with Neptune, through a lens that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant shifts in the distant future due to the continued gravitational interactions between it, Neptune, and the rest of the solar system. In conclusion, Pluto's orbit is a fascinating case study in the complexities of celestial mechanics and orbital dynamics. While current scientific understanding suggests that Pluto is unlikely to collide with Neptune, the future remains uncertain. As space exploration and our understanding of gravitational forces continue to advance, we may gain further insight into the long-term behavior of these distant bodies. Until then, the mystery of Pluto and its potential future interactions with Neptune will remain a captivating subject for astrophysicists and space enthusiasts alike. As we continue to study Pluto's orbit, it becomes clear that the factors influencing its path are far from simple. The interactions between Pluto, Neptune, and the other giant planets in the solar system form a delicate balance that has allowed Pluto to avoid colliding with Neptune despite their intersecting orbits. Yet, this balance does not come without its complexities and potential risks in the distant future. The gravitational pull of the outer planets, particularly Neptune, plays a major role in keeping Pluto on its current path, but as astrophysicists like Neil deGrasse Tyson and Michio Kaku point out, these interactions are not static, they are constantly evolving. One of the critical aspects of this evolving dynamic is the fact that the orbital paths of Pluto and Neptune, despite appearing to cross, are locked in a sort of cosmic dance called orbital resonance. This resonance ensures that for every 2 orbits that Pluto completes around the Sun, Neptune completes 3. This seemingly simple relationship is a result of gravitational forces that prevent the 2 planets from ever being in the same place at the same time. This unique resonance has been studied for decades, and it is believed to play a major role in maintaining the long-term stability of Pluto's orbit. But as Tyson and Kaku have suggested, while these forces are stable for now, the future of Pluto's orbit could be more volatile than we expect. The solar system is not a static system. It is a place of constant motion and gravitational influence, and even small changes can have profound long-term effects. The 3-body problem, which deals with predicting the motions of 3 celestial bodies under mutual gravitational attraction, is a critical area of study when it comes to understanding Pluto's future. In the case of Pluto, Neptune, and the Sun, this problem suggests that while the planets' interactions currently prevent a collision, their gravitational pulls could shift in unpredictable ways over the eons, potentially causing drastic changes to Pluto's orbit. There's also the matter of the larger environment of the solar system to consider. Over millions and billions of years, the positions of the planets will continue to change due to gravitational interactions with one another. Even Jupiter, the largest planet in the solar system, has a significant influence on Pluto's orbit. Its massive gravity helps stabilize Pluto's path and keeps it from spiraling into Neptune or being ejected from the solar system. However, this influence could change over time as the planet's orbits are affected by the gravitational forces from nearby stars or other cosmic events. Moreover, the future trajectory of the solar system as a whole is not set in stone. One of the major concerns for the distant future of all the planets, including Pluto, is the gradual aging of the Sun. As it nears the end of its life cycle, the Sun will eventually expand into a red giant, engulfing the inner planets and significantly altering the gravitational balance in the solar system. While this event is billions of years away, it serves as a reminder that the solar system is in a constant state of flux, and even the most stable orbits could be disrupted by such monumental changes. The possibility of Pluto colliding with Neptune or experiencing some other dramatic shift in its orbit is therefore not entirely outside the realm of possibility. In fact, There are theories that suggest that Pluto's orbit might be influenced by more than just the gravitational forces of Neptune and the other planets. Some researchers propose that distant objects in the Kuiper belt, such as other trans-Neptunian objects, TNOs, could also play a role in altering Pluto's trajectory over long periods. As these bodies interact with Pluto, they could nudge its orbit in ways that we currently cannot predict.